There is a very new concept in Go language which are called generics. Which are called generics. And in order to understand why do we have generics and why did we need generics in the first place, let's see how did we get there. So in this example, we have two functions. We have index int and we have index string. And index int returns the index of x in a slice of integers, or -1 if it is not found. In the same way, index string returns the index of x, a string, in a slice of strings, or if it is not found, then it returns -1. A typical implementation of finding index of a integer or a string. Now, what does the implementation look like? We are ranging through this slice of integers. We are ranging through it, and we have the key here, we have the index here, we have the value here, and we are checking for each iteration. We are checking if the value is equals to x, if the value is equals to the target. If it is true, then return that index, this index. And if the loop finishes and we reach the end statement, we are returning -1. The same way, this is what you notice here. In the same way, we have this code for I, v are ranging through the slice of strings. The only difference between this function and this function is here it is a slice of integers, and here it is a slice of strings. That is the only difference we have. Here the target is an integer, here the target is a string. Now we are doing the same operation. We are trying to find the string. If it is found, we are returning the index. If it is not found, then we are returning -1. Now, how are we using it? Here we have a slice literal with a couple of integers, and we are calling this function with this slice and a target 15, and output is 2. Same way, we have a slice literal of type string, and we have 3 strings, and we are passing hello, which is not in the slice. That's why we'll get output -1. Now, the thing to focus here is we have two different functions which do the exactly same thing. The operations are very similar, almost exact. The only difference is their types, these types. Here it is an integer, here it is a string. Now, and because they are of different types, we had to write the same implementation twice, and that increased the boilerplate code. And this is the reason we have generics. Generics help us reduce this boilerplate code by providing what we call type parameters, which basically means we can use types as parameters. As far as now, until now, we have been using values as parameters. Now with generics, we can use types as parameters. So let's look how using generics, we can reduce this code. Here we have gotten rid of those two functions, index integer and index string. Now we have a single function which is called index. Now there are 3 new additions here. What we are doing here, the first part, this is where we declare the type parameter, where we pass the type. Okay. And here we are saying we are declaring a parameter called t. You can imagine it as a declaration. We are declaring a parameter called t, which has the constraint comparable. Now this basically means the type has to satisfy the constraint comparable, which basically means that whatever type it is, it has to be comparable, which means it should be able to compare with, like it should satisfy the equality operator. We should be able to use equality operator on that type. That's what we are saying. We are putting one constraint on this type, that it cannot be any type. It has to be comparable type, which means it has to work with the equality operator. Okay. Now this is the type parameter declaration. Now, once you've declared this parameter here, now we can use it in the function parameters. This is the type parameter, this is the function parameters. Here we are saying whatever type is provided here, we are taking a slice of that type, and in the next parameter, a single variable of that type. Here it is a slice of that type, it is a single variable of that type. All of this will be dynamically assigned during compile time. Here we are just saying it can be any type as long as they are comparable. Okay. Now after this, pretty much the implementation is same. We are looping through it and we are checking checking it, and if it's true, we're returning the index, otherwise we are returning -1. Now, how does this work? Here we have a slice slice of numbers, and we are passing this slice to index, which is a generic function. Now, in the same function, we pass a slice of integers, and to the same function, we pass a slice of strings. And because it is a generic function, and we did not have to assign, we did not have to explicitly pass the type of t. We did not have to say that here t is a integer or here t is a string, because in most of the cases, Go compiler is smart enough to derive, to infer the type. Whatever type we are trying to assign here, it is able to infer that type using these two. It checks that SS is a slice of strings and this is a string. And using that, it can deduce that in this function implementation, the t will be string. And using this nice feature, now instead of two functions, we have one function, one generic function, which can handle both string type and integer. That's one use cases of generic function. Now, generic are a pretty new addition to the language. They were not there from version 1, and they were added later on. So you might not use generics as extensively when you are starting out, but you will definitely see different implementation, different use cases of generics. That's why it's a good thing to understand why do we have generics and what do they do, how do they work. And there isn't a lot of things in generics, as long as you understand that we have type parameters, and we can use that type parameters in the return type also and in the function parameters also. And using this feature, we can reduce some amount of boilerplate code as long as the implementation is the same, as long as the function body looks similar for two functions. That's a typical use case of generics. That's all we need to know as of now. We'll see more generics as we proceed through different resources. Now, finally, we reach concurrency. One of the strong points, one of the strong selling points of the language Go. And there is a lot to say and there is a lot to understand in this topic. And as I said in the initial part of this video, this is one of those topics in the language where if you're a beginner, you should not try to understand everything. If you do that, that will only intimidate you. Of course, if you get all the concepts and if you're comfortable with all the concepts that Go has to offer in this topic, then that's fine. Then that's great. But if you don't get it, then that's also fine. If you get some of it, then that's fine. If you don't get any of it, then that's also fine. We'll explore more and more resources later on in this series, and eventually you'll get it. Eventually you'll get the hang of all the constructs that Go has to offer in this area. Okay, with that, let's jump into this example of Go routines. Now, what's happening here? We have a function called say, and it is taking one string. It is taking one string and it has a for loop. Inside the loop, it is looping 5 times starting from 0 to 4. And in each iteration, it is blocking the execution. Time.sleep blocks the execution and it is blocking for 100 milliseconds. We have a constant called time.millisecond for each millisecond, and we are blocking for 100 milliseconds in each iteration. And after blocking for 100 milliseconds, we are printing that string, whatever string that has been passed to this function. Now it happens 5 times. For each function call, it happens 5 times. Okay, now what's happening in the main function? In the first line, we have this function. We are calling this function, but before that, we are adding this prefix called go. And then in the next line, we are calling this function normally. Now, what does this go do? This syntax, go and then calling a function, this actually spawns a new Go routine, which runs concurrently with the main Go routine. Now, there are some concepts to understand here. In every Go program execution, whenever we are running a main function, a new Go routine is created. It's called the main Go routine. And everything that gets executed sequentially that happens in the main Go routine. So this part, the say hello, the normal function call, and all the examples that we've been seeing so far, all of them have been executing in the main Go routine. Now, Go provides us this construct called Go routines. Then what is a Go routine? Go routine is basically similar to a thread that are offered by other programming languages, but it is very different from a thread. To wrap your head around the concept, you can think of it as a thread, but Go routine is something that is managed by the Go scheduler. It is managed by the Go scheduler. It is not managed by the operating system. Now, that's one thing that is a difference between a Go routine and a concrete operating system thread that is offered by other languages. Number one, they are not managed by the operating system. They are managed by the Go scheduler, the Go runtime. Go has a dedicated component, which is called a scheduler, and that manages all the scheduling and running of Go routines, the blocking of Go routines and everything. Number one difference is Go routine is managed by the scheduler. Second, one of the advantages of using Go and using concurrency primitives in Go is Go routines are very lightweight. Very lightweight. And what do you mean by lightweight? Typically, when we spawn threads in other programming languages, which are operating system threads, threads are pretty heavy. A typical thread, depending on the implementation, depending on the language, they might range from a 256 KB to 1 MB of memory in stack. Now each thread takes up this amount of memory. Now, on a high level, this might not seem a lot, but when you spawn a lot of threads, then it can cause your system to run out of memory, and it can cause memory leaks and a lot of problems if you are not managing your concurrency workflows efficiently. Now, Go routines, which are provided by the Go runtime, they are advantageous in this scenario because they are very lightweight. A typical Go routine has a size between 2 KB to 4 KB, a starting size, and they are dynamically resized, which means they are not fixed. Depending on the requirements of the Go routine, depending on the memory requirements, the allocation requirements of the Go routines, they can resize themselves up to whatever size they're needed, from hundreds of MBs to GBs, depending on the system requirements, until the system runs out of memory. Now, that is the second advantage. Go routines are very lightweight, and Go routines are managed by the Go scheduler instead of the operating system. Those are 2 points. Now, that's about Go routines. But why do we need Go routines in the first place? Go routines are the Go's way of providing concurrency features. Now, what do we mean by concurrency? Now, a lot of languages provide concurrency in their own way. JavaScript provides concurrency using the construct of event loop. And different languages have different implementation of the concept concurrency. So what do we mean by concurrency in the first place? Concurrency is basically managing execution of different tasks efficiently so that it does not block the system flow. Now, that is a very abstract definition of concurrency. Now, whenever we talk about concurrency, a different topic also comes into discussion, which is called parallelism. There are a lot of resources. There is a lot of debate surrounding the difference between concurrency and parallelism. And you can explore that to understand the concepts that surround them. But on a very high level, parallelism is a hardware feature we can imagine, and concurrency is a software feature. It is something that is provided by your language, your software, your system, is an operating system, whatever. And parallelism mostly depends on your hardware, depends on your CPU cores. How many CPU cores do you have? Because concurrency is executing tasks in the most efficient order to have the minimum amount of latency, to not waste resources of CPU, to not waste resources of memory. Okay. Concurrency does not mean that two tasks are being executed parallelly. Okay. Concurrency basically means if you have, let's say, 4 tasks all spawned at the same time, then depending on your system's implementation and depending on your language handling capabilities, those 4 tasks might get executed in any order. The order is not specified when we are talking about concurrency. Now, these 4 tasks can be executed in any order. The first, the second, the fourth, then the second, then third. At a time, one task might be executing, and if your system supports parallelism, then at a time 2 tasks or 3 tasks might be executing. But that is completely different from concurrency. Concurrency is basically executing your tasks in a most efficient order. The order is not specified. It depends on your implementation. It depends on the programming language. But parallelism is truly executing tasks in parallel. Like both tasks are getting executed in parallel in your CPU cores. Okay, that's basically a high-level introduction of concurrency versus parallelism. And now, as I said, there are a lot of resources that you should explore. A lot of resources in YouTube. For example, very good talks by Rob Pike, one of the co-founders of the Go programming language, and a lot of other resources that you should definitely explore. I don't have the capability and definitely don't have the time to get too deep into the concurrency philosophies and the parallelism versus concurrency debate. So this definition should be enough. Now, circling back to where we started from, Go routines are Go's way of providing concurrency features to the users of the language. Now, Go routine is the primary component which provides the capability of concurrency. And the thing to remember is every Go program execution starts with the main Go routine, and other Go routines are spawned from the main Go routine. And the moment the main Go routine returns, the moment the main function returns, all the Go routines are abandoned and they will be collected by the garbage collector and all. But you won't see the execution, the results, whatever you are expecting from them, because as long as the main Go routine is running, all the other Go routines are executing in concurrently with the main Go routine. So you can imagine it as this is the main Go routine and this is the execution flow of main Go. And during the execution, we can spawn different Go routines from main. For example, we spawned 2 Go routines here from main. Okay, and those Go routines can spawn more Go routines during their life cycle, and it can go on and on. But at the end, the main Go routine has to wait for all these Go routines to finish. Otherwise, you won't see the results. You won't see whatever results that you are expecting from these executions. Even though these Go routines are running concurrently with the main Go routine, they cannot run independently outside of the main Go routine. They depend on the main Go routine to wait for them. That's something to remember. Now, with that basics, now we can jump into the example of what's happening here. We have a function and we have the syntax called Go. And whenever we call a function with this syntax Go, this language spawns a new Go routine which executes concurrently with the main Go routine. Now, when we run this example, this is what we see. Now, other thing to remember is once you spawn a Go routine, there is no guarantee. There is no way to know for sure that if this Go routine started executing immediately or if the next instruction, whatever the instruction in the main Go routine executed at that point of time. You cannot say. The moment you spawned a Go routine, there is no way to know for sure that which statement executed first. Now we can just imagine to distinguish between those two. In the Go routine that spawned from the main one, we are printing world. We are printing world 5 times with a blocking time of 100 milliseconds between each iteration. And in the main Go routine, we are printing hello 5 times with a blocking time of 100 milliseconds with each iteration. Now, if we look at the results, this is what we find. First, we see world, which means The moment we spawned this Go routine, it started executing immediately after the 100 millisecond blocker. Then we see world, then we see hello, then we see world, then we see hello, then we see world, then we see hello, hello. So if you look at it, there is no specific order. As I mentioned, concurrency means the order is not specified. It depends on your implementation and it depends on your language. Now Go promotes this philosophy, CSP, communicating sequential processes, which basically states that which is very different from how other programming languages approach concurrency, which is basically by sharing state. Now Go promotes a different philosophy which states that don't communicate by sharing memory, share memory using communication, which is a very abstract way of saying instead of using shared memory or shared state to implement concurrency, you should depend on communication between different threads, or in this case, communication between different Go routines to implement concurrency. Do not share memory, because sharing memory for historical reasons, from historical evidences, we have experienced that sharing memory or sharing state gives birth to a lot of problems if you are not someone who is expert at implementing concurrency primitives. Problems like starvation, problems like deadlock, and all these problems can be avoided using communication as the means of concurrency implementation. Now, all of those problems do not just go away, but the philosophy, the mindset of sharing state using communication can prevent a lot of those bugs. It does not prevent all of them, but the way they are structured, the way they are implemented, the way they promote people to use it, they can avoid a lot of those bugs. There is a very small room for making classical or historical mistakes when it comes to concurrency. That's why Go has this primitive, Go has this construct called channels. And channels are, in one line, channels are data types. They are data types which allow two Go routines to communicate with each other, which allow two Go routines to send data to each other. That's a very revolutionary idea, and you can do your own research to study all the materials surrounding it. But that's the philosophy behind it. Instead of sharing state, instead of implementing mutual exclusion, Go also has construct for classical implementation of concurrency for like concepts like mutual exclusion and mutexes and semaphores and all. But Go promotes heavily the idea of channels. And the idea of channels are, in most of your concurrency based implementation, try to see if you can solve the problem using channels, which basically means try to see if you can solve the problem using communication between two Go routines. Instead of using primitives like semaphores and mutexes, try using communication as your first approach to solving concurrency based problems. That's why we have channels, which are basically data types, so that two Go routines can communicate between each other. Now that's what's happening in this example. Let's explore this. We have a function called sum, which takes a slice of integers called s. In the second parameter, we have a variable called c, which is of type channel, and it is a channel of integer, which means a channel is basically one hierarchy above other data types. So a channel can be thought of as a container. Channel itself is not a data type. Channel can be thought of as a container data type, and you have to specify what kind of data goes inside the channel. So if we think about channels, if we think of channels as these tunnels, we have one Go routine and we have other Go routine, and we want to send data. Okay, we want to send data. Data might be this side, that might be this side, and this data we have to specify what kind of data goes in these channels. So it can be integer, it can be string, it can be any kind of Go data type. So a channel has to specify what kind of data goes inside the tunnel, what kind of data Go routines will send each other. That's what we have this integer. This basically says this is a channel which will have integers inside it, which basically go routines will send integers using this channel, using this tunnel. Now inside this function, we are declaring a variable called sum, and then we are ranging over this provided slice, this slice of integers, and we are basically calculating the sum and storing it here. Then after we are done, we are sending the result into this channel. As I said, channels can be thought of as a tunnel where we will send data. Two coroutines will send data to each other using a channel. That's why after we have this result, we are sending our data through this channel or this tunnel. You can imagine channels as tunnels. You are sending the result into this channel. Now, another thing to focus here is this signal, this part. We use this construct, this angular bracket and a hyphen to send data to a channel. This is the syntax that you have to remember. Now, moving on, then we have the main function, which is the entry point of our program. In our main function, we have a slice of integers, positive and negative. Then we are declaring a channel. Now, as I said, channel is one of the reference types. We have 5 reference types. We have slices, we have maps, functions, channels, and pointers. And channels are one of the data types which are of reference types. And as we know, reference types can be declared with a make syntax. So we declare a new channel with make, and we say it is a channel of integers. Then what we do, we spawn 2 go routines. As we saw in the previous example, we can spawn new go routines from the main go routine using the syntax called go and the function call. What you're doing, we are taking, since it is a slice of 6 integers, we are taking the first part of the slice, starting from the start to the first half. We are sending this 7 to 8 in the first function call. So we are trying to find the sum of the first half, and in the second function call, we are trying to find the sum of the second half. We are spawning these 2 go routines. Now this is the important part. We spawn 2 go routines and we pass this channel, we pass this tunnel, we pass this data type using which those go routines can send data to our main go routine. As I said that main itself is a go routine, and all the go routines are spawned from main. And since we know that channels are a means of communication between 2 go routines, what we can do, we can spawn different go routines from main, and we can use channels to send data, to send signals to our main go routine, to our main execution. And that's what we are doing here. We created a channel which is of type integers, which basically means we can only send integers to this channel. And we spawn 2 go routines which call 2 functions which are running concurrently with the main function. Now in this line, what we are doing, we are declaring 2 variables x and y, which is a short form declaration, and we are receiving data. We are again using this syntax. We are receiving data from this channel, which is the variable c, which we pass to these 2 function calls with the go routines. We are receiving from this channel using these 2 variables twice. So basically we are saying we want to receive 2 values. We want to receive 2 values from this channel, and then we are printing it. We are printing x, we are printing y, and we are printing sum. And if we run this, we are getting the sum of the first half, and then we are getting the sum of the second half, and then we are getting the result of x plus y, basically the sum of all the elements. Now, what are we trying to do here? First thing, we are trying to divide our work. We are trying to divide our work between 2 go routines. If we just call the sum function without spawning a new go routine, we just call the sum function in the main go routine. If we did that, then it will just go through all the elements and give us the sum. Now, since we know using concurrency, we can divide our work as long as the order is not specified. That's the important thing to remember. As long as the order is not specified, we can divide our work using concurrency, and we have go routines to implement concurrency. That's the reason we spawned 2 go routines and we divided our work. We called the first go routine with half of the elements and the second go routine with half of the elements. Then this is the important part. We waited, as I mentioned earlier, if the main go routine does not wait for all the go routines that were spawned from the main go routine, then the execution will stop. Then we will never find the result. So channels, receiving from a channel is a blocking execution. You should remember this. Receiving from a channel is a blocking execution. And since we tried to receive here twice, then we got the value of the first go routine, which tried to send some value into this channel. And then we got the value of the second go routine, which tried to send some value into this channel. And we received twice from this same channel. And that's the reason the main go routine did not end. The main go routine waited for these two go routines to end because of these channels. Now everything comes together. We have go routines. We have go routines to spawn, to divide our work, to have the capability of concurrency. And we have channels. We have channels to synchronize or to orchestrate or to communicate between these go routines, whatever you can imagine. There are a lot of use cases of channels. There are a lot of implementation, a lot of starting from basic to very complex implementation. And this is a very simple example of using channels to orchestrate different go routines because of the property that in the main go routine, as long as you're receiving from a channel, it will block. Now we have two types of channels. One is called a unbuffered channel and the second one is buffered channel. And the high level difference between these two are a buffered channel acts like a queue. We have a queue here, and if we have a buffered channel and we have a go routine, so the go routine can push values into this buffer or a queue. Let's say this size of this buffer is 4. So this go routine can keep pushing into this queue until the size is filled. So it can push 1, it can push 2, it can push 3, and it can push 4. And until the buffer is full, this go routine, whatever go routine it is, it can keep pushing into this channel and it won't have to block the execution. And on the other side, if there is another go routine which is receiving from this end, which is receiving from this same channel, then the whole workflow will go in a very nice way, because the producer, we can think of this go routine as a producer and this one as a consumer. The producer can produce at its own pace. It won't have to wait for the consumer to take out the data. It can keep pushing and the consumer can consume at its own rate. So there are no blockers here until the buffer is full. But in a unbuffered channel, we don't have a queue. We just have a tunnel. There is one go routine, is the producer, and there is another go routine, is the consumer. And this interaction will block. Let's say this go routine has a value to send, which is called 1. This is the value it wants to send. So until this receiving go routine takes this value, until both of these are in sync, until this tunnel is synchronizing, this interaction will block. So on a high level, as you can see, buffered channel has a little flexibility, and whenever we have a producer and consumer based scenario, then the pace of producing, the pace of sending is different to the pace of receiving or the pace of consuming. Then we can go with a buffered channel. Or if we know the maximum size of this channel, if we previously know what is the maximum size of this channel going to be, how many values that we will be needing in future, in those cases we can go with a buffered channel. And since we have the construct of make, which provides some kind of capacity during initialization, as we saw with slices, as we saw with maps, in the same way, using make, we can assign a predefined capacity to a channel, and that channel will be a buffered channel. It will have a queue. It will have some kind of storage mechanism so that the interaction does not block. That does not mean that we should always use buffered channels. Sometimes we also need unbuffered channels, which causes the interaction to block. And because the interaction is blocked, unbuffered channels are mostly used for synchronizing. When the property of synchronization between two Go routines are of utmost importance, or if we need the property of synchronization, if we need the property of blocking, then that's the scenario we go with unbuffered channels. We don't want any queue, we don't want any buckets, we don't want any storage mechanisms, we just want to synchronize two Go routines. On a high level, those are two different use cases of unbuffered channels and buffered channels. And in this example, what's happening? We are creating a channel which has a capacity of 2, and we are using the make function to create this channel. And this 2 is basically the size of our queue. It can maximum push 2 elements, and until the buffer is full, until it has 2 elements, we can keep pushing to it. And that's what we are doing here. We are pushing the first value, we are pushing the second value into this channel. And in the print statement, we are waiting for this value. Okay. And if you try to run this example, we get 1, 2 as expected, nothing special. We just explored this example to look at the two different types of channels. One is unbuffered channel, the second is buffered channel. Now, in this example, we have a couple of new concepts. We can see there is one, we are using close. The second one, we have a range. Instead of ranging over a string, instead of ranging over a slice, we are ranging over a channel. Now, what's happening here? So we have some notion about Go routines and channels and the main Go routine blocking and all. Couple of properties to keep in mind while we explore this example is, first one, main Go routine has to wait until all the Go routines are finished executing, until all the values are received from the channel. Basically, main Go routine has to wait. Otherwise, the Go routines that has been spawned from the main Go routine, they will never finish executing. That's the first thing. Second, we already know that channels are used to communicate between two Go routines. They are some kind of tunnels to communicate between two Go routines. Now, in some scenarios, you might ask the question, if two Go routines are communicating, one is sending, one is receiving, or other one is receiving, other one is sending. In those scenarios, how will the other Go routine know that the sending has been finished? Or when will it stop receiving? When to stop waiting for values in this channel? That's the reason we have this function called close. And this function is a predefined function provided by the Go runtime, which is used to send a broadcast signal to inform the parent Go routine that the sending has been finished. We don't have any more values to send in this channel, so that you can stop receiving, you can stop blocking the execution. Those are the two concepts that we will focus in this example. Now what's happening here? We have a function which calculates the Fibonacci series, and it takes one integer and it calculates the Fibonacci series up to that integer. We already know what is the Fibonacci series. We basically have this series 0, 1, and you add these two numbers, we have 1, and you add these two numbers, you have 2, you add these two, 3, then 5, then 8, then 13. This is basically a Fibonacci series. It's a mathematics concept, and that's all you need to know. What is a Fibonacci series? What's happening here? This function basically calculates the Fibonacci series. It declares two variables x and y. They start with 0 and 1, and it loops until the number n, whatever you provided. How much to extend the series? That is basically the number n. It loops until that number, and in each iteration, it sends the current value. Basically, first it will send 0, then 1, then 1, then 2, then 3, then 5, then 8, then 13. It will send all these numbers in the Fibonacci series one by one into this channel. That's what it's doing overall. But in the end, it is calling close. So let's say we have provided the number 4 in n. What will happen? In the first iteration, the I will be 0, and it will send the value of I. to this channel. So we have this channel, and this channel has the capacity of 10. It has the capacity of 10, so it can maximum hold 10 values at a time. As long as there is a receiver taking values out of it, it can hold any amount of value. But at a time, maximum amount of value without any receiver taking out values from it, it can hold 10 values. The capacity is 10. Now, first, in the first iteration, it sends 0. It has 0. Then in the second iteration, I has 1. Then it sends 1. Then in the next iteration, 1, then 2, etc., etc. This is how it works. In the end, since our value of n is 4, and maximum it will run 0, 1, 2, 3, 4 times. It will run 4 times. After it is done, after this for loop ends, it calls close. Now, the reason we need this close is because after this loop ends, we want to inform the channel. We want to inform the main go routine or whatever the parent go routine is that we are done. We are not sending any more values. And that's the reason we need this close. And when we close this channel, it sends a signal to the main go routine, and we'll see how that signal works. It sends a signal to the main go routine that you now can stop receiving. You can now stop blocking. Now what happened here? It finished the loop, and in the end it called close. Okay, that's done. Now coming back to this line. Here what's happening? We are ranging over a channel. Now in Go, you can range over a channel which does a couple of things in the background. What it does, when you range over a channel, it sequentially receives. It takes out values from those channel as the other go routine is sending the values from the other side. It takes out values in that order from that channel until a close is called on that channel. Now those two properties work very nicely. The range loop on a channel basically does two things. It takes out values from a channel sequentially so that you don't have to manually take out one value. You basically do not have to run a for loop yourself. If we did not have this construct called ranging over channels, what you would have to do, you have to do a for loop, and you have to keep the maximum range of that for loop as 10, and you'll do a traditional for loop, and you will receive from that channel 10 times yourself. Now, because of this construct called range, now we don't have that boilerplate code anymore. This basically ranges over this channel. It takes values serially from that channel as the other go routine is sending values from the other side. And when the other go routine calls close, it stops receiving. Okay? It stops receiving. The range also does this. The moment close is called on the channel, it stops receiving and will exit out of this main function. And what happens if we run this? We can see the Fibonacci series up to 10 integers as expected: 0, 1, 1, 1, 2, 3, 5, 8, 13, 21, 34. Okay, those are two new concepts. We can use close to inform all the go routines that are receiving values from this channel that we have stopped sending values. Now you can stop receiving one thing, and we can use range to sequentially, serially take out values, receive values from a channel. Okay, those are the two things in this example. Because of our needs of synchronizing different go routines using channels, Go also provides us another nice construct which are called select statements, or selecting on channels. How does it work? Here we have a function called Fibonacci again, and it is taking two channels, one channel called C and another called quit, and both are channels of type integers. We can only send integers in this channel. Now initially it is declaring two variables, x and y, and it is doing all the x and y, and then it is doing an infinite loop. It is starting an infinite loop. As I said, as we have discussed before, if inside a for loop we do not have a condition, then it is by default an infinite loop. Now there is nothing to worry here. As I said initially during the start of the video when we were discussing for loop, there are uses of infinite loops in Go, especially in the concurrency section, and this is the first time we see it. We have an infinite loop here, And what's happening inside the infinite loop, which this infinite loop basically means this will not stop executing until there is an explicit return or an explicit break. And we have a return in this. Now, inside this for loop, we have a select statement. Now, typically we use select to do different case checks and run executions depending on those case checks. In this area, in this application, what we are doing a select statement without any expression initially. There are no expression initially. There are two cases. First case, we are sending the value of x into this channel called C. This is the first case. This is an expression. As we already know, in select cases in Go, we can do expressions. It does not have to be constants like strings and integer. We can call expressions. And in this expression, we are sending the value of x into C. And inside that, what this basically means, if this is successful, if we can send it, then this gets executed. We assign y to x, then we assign x plus y to y. We also have another case. You'll see how these cases work together. We have another case where we are seeing if any value from quit comes. We have a quit channel, and if we receive any value, it does not matter in what value it is, as long as it's an integer. As long as we receive any value, any integer in this channel, quit channel, will print quit and will return, will break this loop. That's what's happening in this function. Now coming back to the main function, we are initializing one channel for C, another channel for quit. Both are of channels of integers. Then we are spawning a Go routine. And this is another concept here of anonymous functions. In Go, since we know that functions are first class citizens, you also can use anonymous function calls. So you can just write Go instead of creating a function somewhere else, naming it and then calling it here. You can literally define the function and call it at the same time. And it's called an anonymous functions. And what this function does, we are spawning a new Go routine and we are calling this function in that Go routine. What this function does, it loops from 0 to 10. So starting from 0 up to 9, loops from 0 to 9. And with each iteration, it receives from the channel C. It receives from the channel C in each iteration. Basically, it receives 10 times from the channel C. Then after the loop is finished, after we are done from 0 to 9, it sends one value, the value of 0, into the quit channel. As we said, quit can take any integer. So we are sending the value 0 into the quit channel. That's what's happening in this Go routine. Then in the main Go routine, we are calling Fibonacci. Now, these two functions, Fibonacci, in the main Go routine, we have the main Go routine here. That's how execution is working. From the main Go routine, we are spawning another routine, which is basically doing this for loop thing. This is happening here in another Go routine. And these two are executed concurrently because of how Go routines work in Go. Now, in order to communicate between these Go routines, what we have channels that we have already discussed before. And how are channels working here? We have two Go routines, and what's happening in this Go routine? We have two Go routines, one main and one that is spawned from main. In the main Go routine that is being executed, which is basically here, this function call, what's happening? We are sending the value of x with each iteration. We are sending the value of x to this channel, to the channel C. Now, the way select works with channels is it checks different case statements at the same time. Of course, concurrently, but you can imagine they are happening at the same time. Now, because both of these checks are being run concurrently, what happens is, as long as we can send values to C, as long as we can send the value x to C, and because C is an unbuffered channel, and in the spawn Go routine, we are receiving 10 times. In the spawn Go routine, we are receiving 10 times, and since C is an unbuffered channel, here until we reach the value of 10, x can be sent to C. X can be sent to C. But the moment this for loop ends, this go routine sends a value to quit channel. And what happens? The moment it receives a value in this channel, the moment this case gets executed, it keeps checking both the cases at the same time. That's happening. But it is not coming inside. It is only coming inside because we can send value of X to C with each iteration of I here. So both of these are being run concurrently. It's a little hard to imagine it, and that's fine. Just try to follow me, and it's fine if it does not make any sense. It's just an example to show the use of select and how select works with channels. You don't have to exactly understand how everything is working. You just have to understand the concept that we have a select block and we can orchestrate channels using selects. So we are just going through concepts. You don't have to master concurrency at this phase. Okay. Now both of these are being run at the same time, and the moment this block is true, the moment this block satisfies, the moment we receive some value in this channel, because we are trying to receive from this channel using this syntax, the moment it happens, we come inside, we print quit, and we return. This loop breaks, and the moment this loop breaks, we get out of the main go routine. As I said, the moment you get out of the main go routine, all the go routine stop executing. Okay. Now, what happens if you print this? Let's print this, and as you can see, with each iteration, we are receiving the value of X into this, and we are printing it 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. And in the end, the moment we send the value 0 into quit, it reached here. This statement became true, and it came inside, it printed quit, and it returned, and this loop broke. And the moment this loop broke, we came here and we exited out of main go routine. And that's the end of our program execution. Now, this example was just to demonstrate the use of select case and the use of the infinite for loop and how they work in the concurrency space. Now, for us to understand how select works in a much deeper way, in a little deeper way, we have another example. What's happening here is we have one variable called tick, and it is using the standard library package time. And time has different functions for different things. Tick basically provides us a channel. So these two variables are channel types. They are provided to us by this function tick and this function after. Now what's happening here is what we're saying, every 100 milliseconds, this tick function, because we initialize this variable using this tick function, every 100 milliseconds, this channel will get triggered. Will receive a value in this channel every 100 milliseconds. So it is kind of an interval running. Every 100 milliseconds will receive a value in this channel. Any value, does not matter. It's just an interval counting. Now we have a second variable called boom. And this channel, what we are saying, after 500 milliseconds, send a value to us using this channel. This sends a value every 100 milliseconds. This sends one value once after 500 milliseconds. Now what's happening? We have the same infinite for loop and select case construct here. We are blocking here with this for loop. So this main go routine will not exit. This main go routine will not end unless we break out of this infinite for loop. That's the use of it. And what's happening inside this interval? What's happening inside this infinite for loop? We are doing the select case. Inside selects, we have three cases. One case, if we receive a value in the tick channel, will come inside and will print this. If we receive a value in the boom channel, will come inside, will print this and will exit. We'll call return. The moment we call return, we exit out of this for loop and we exit out of this main go routine and the program ends. So this is our ending statement. The moment we receive a value in this boom channel, we will exit out of this for loop and we will exit out of this main go routine. But there is another case here, which is the default case. And this is provided by select. If this is false and this is false, we will reach here. So this is an iteration. We are inside a loop. So we are going through infinite iteration. We are repeating the cycle. In one iteration, it checks this. Then it again starts, it checks this, again starts and it checks these. That's how it works. So in every iteration, if this is false, then it executes this. Again, in the second iteration, if this is false, it executes this. In the third iteration, if this is true, then it executes this and continues to the next iteration. That's how this infinite for loop and this select case works. Now, in the default case, what happens? We print this and we sleep for 50 milliseconds. We block the execution for 50 milliseconds. Okay. Now, when we executed it, this is what we got. Since we said we send as a value every 100 milliseconds, in the first iteration, 100 milliseconds is not done yet. That's why this is false. And this is of course saying send as a one value after 500 milliseconds. So this is also false. That's why we reach the default case where we print this dot. That's why in the first iteration, we see this dot and we sleep for 50 milliseconds. Now we sleep for 50 milliseconds. Now, when we reach here, second time, at this point, in the first iteration, we run the default case and only 50 milliseconds is done. Now, in the second iteration, what happens? We again come here, we check if we receive a value from tick, it is only 50 milliseconds. We only receive a value every 100 milliseconds. That's why this is false. This is obviously false because it's only been 50 milliseconds. We will only receive a value after 500 milliseconds. Okay. Now this is also false. We again reach the default case and we again print a dot. Then we again sleep for 50 milliseconds. Now it is 100 milliseconds. In the third iteration, when we come here, in the third iteration, the 100 milliseconds is over now. Now we should get a value in the tick channel. That's why in this iteration, in the third iteration, this is true. That's why third time we printed tick. We came inside this, we printed tick. Okay. And this is how it works. In the fourth iteration, again, we'll receive another value after 100 milliseconds. And it has only been 100. So in the fourth iteration, we still have 100 milliseconds more to wait until we'll receive a value in the tick channel. And the boom channel is obviously due for another 400 milliseconds. Okay. So that's why we reach default here and we print a dot here. Then we sleep for 50 milliseconds. Then in this next iteration, of course, it's only been 150 milliseconds. So we again reach the default case and we print this dot and we wait for another 50 milliseconds. In the sixth iteration, again, it's now 200 milliseconds over. So we reach the second cycle of this tick channel. Now we'll receive a channel in this tick channel because it's been 200 milliseconds is the next iteration of getting a value from tick. That's why we printed tick again. And we continued the loop. In the next iteration, again, it will reach default and so on, until in the 15th iteration. In the 15th iteration, we reach here. This is false. It's not been 100 milliseconds before, after the previous iteration. And we reach here. Now it's been 500 milliseconds and this sends us a value. Now this case becomes true. And the moment this case becomes true, we come inside, we print this boom and we call return. And because we call return, we break out of this infinite loop. And the moment we break out this infinite loop, we reach here. And this is the end of the main function. And the moment we end the main function, our program stops executing. That's why this is the result we see. Now here we have a struct. Inside the struct, we have a field called v, which is of type map. And in this, the key is string and the value is integer. And this struct has two methods. One is increment and one is value. Increment basically mutates the value of the map and we are using pointer receiver so that whatever mutation that we are doing here, it shows up in the original instance. And this value method returns the value of that key. Okay, that's this part. In the main function, what you're doing, we are initializing this struct with make function for initializing the map. And we are starting a loop. And this loop will run for 1000 times. This will run for 1000 times. And in each iteration, it spawns a new go routine. It spawns a new go routine, which calls the increment method for this key. And this thing happens for 1000 times. So ideally, 1000 go routines are spawned from the main go routine and each go routine increments the value of this map for this key. In the end, we are calling time.sleep because, as we already know, if the main function exits, we will never see the results of the spawned go routines. That's the reason we are simulating. We are simulating the blocking of the main function. Ideally, we should use a channel or a wait group. We have not explored wait groups yet, but we'll explore them later. We should ideally use a channel or a wait group to block the main function. But for the sake of this example, we are using time.sleep to block the execution of the main go routine so that we can see the results of all these 1000 go routines. And in the end, we are fetching the value of this key from this map. Now, ideally, what should happen? 1000 go routines are spawned and all of them are incrementing the value of this key. So ideally, it should start from 0 and by the end, it should have the value 1000 because we spawned 1000 go routines and each go routine incremented the value by 1. Ideally, we should have 1000. But what happens if we run this? When we run this, we get this error. And when we go to the top, it says concurrent map writes. And what that means is we spawn 1000 go routines and all the go routines are trying to access, they are trying to write a value to this map in an unspecified order. And because of that, Go was able to detect that there is a problem in this program. When you are working in the space of concurrency, you have to constantly think about orchestrating state between your go routines. So this is a classic example of that. You have different go routines, in this case 1000 go routines, and all of them are trying to mutate a value in an unspecified order. And to prevent this case, to prevent this exact scenario, we have a construct which are called mutex. Mutex basically, it's a concept from operating system if you have studied. Mutex, what they do, they are basically gatekeepers. They keep the gate, they have an entry point and an exit point. And whatever happens in this area, which is called mutual exclusion area, whatever happens, this is safe from concurrent access so that only one go routine at a time can access this area. It does not matter how many go routines you have. In this case, we have 1000 go routines. Even if you have million go routines at a time, only one go routine can access this area. Okay. And the moment it unlocks, at this point it locks and this point it unlocks. After it unlocks, another go routine can acquire this lock and it can do something and it can then unlock. And with this flow, now we are safe from multiple go routines, all of them trying to concurrently mutate the value of a map. Now what happens? How can we fix this? For this exact use case, Go provides us this package called sync, and inside this sync, we have this value called mutex. Now, inside the same struct, we add this another field called mutex. And now what we do, in the increment method, we lock it. At the start of the execution, we lock it and we mutate the value. After you mutate the value, we unlock it so that this is the mutual exclusion area. At a time, does not matter how many go routines are trying to access this, how many go routines are trying to call this increment method. At a time, only one go routine can get inside this area. And at a time, only one go routine can call the increment function successfully. If not, other go routines will have to wait for acquiring this lock. And only after that go routine unlocks it, another go routine can acquire the lock and it can mutate this. In the same way, if we have the value function and this value function acquires the lock and it defers the unlock function. As we already know, we use defer in different scenarios so that it does not matter when the function ends, in what scenario that function ends. Before the function returns, before the function ends, Go will automatically call this function because we added defer here. That's what we are doing here. We are acquiring the lock and we are saying before this function returns, unlock it. So we are not exclusively guarding what the area is. We are just saying we want to acquire the lock when we enter and we want to unlock it when we return from this function. And in the mutual exclusion area, what it is doing, it is getting the value for that key. Okay. Now we have concurrency safe mutation and concurrency safe access for this map. what happens when we run this now? Let's run this. And as you can see, we have our expected result of 1000. We spawned 1000 go routines and all of them incremented the value for this key once. And in the end, we have the value 1000. And we were able to do that in a very predictable manner, in a very systematic manner, because we have this construct provided by Go for mutual exclusion, which is called sync.mutex. We can guard the access of Go routines using mutexes, and that's what mutexes are used for. And with that, we